Okay, I think I only just reviewed. Oh, why? What happens? Oh, okay, good. Good. I only just recorded this homework discussions, so you do not need to copy now. Okay, so the homework 5, that is the first problem is basically on the I want to show example. You can just finish this. You already know how to just solve this, like in the position representations. I want you to do the similar problem in the momentum representations. It's not much easier for sure, but it's definitely I want to give you another way to solve these problems. So in this case, we want to starting with Schrodinger equations in the momentum representations, right? So I will just so in this way, the P operators is an easy operator, right? And the X operators is a hard one. So you can just copy and paste these from the lecture notes. We already just trying to represent the potentials into the in the momentum using P. So there's no like any X in these equations because X is no longer a valid dynamic variables. So we are starting from here. So this is the Schrodinger equations in the momentum representations. And here the important part is the potential part. The potential part is basically we evaluate that using the, you remember that is when we derive that, we insert like identity operators to converting the position representations to the momentum representations. I think these equations also happens in the lecture notes. Okay, so next we need to just replace this Vx using these delta functions. So that means it is quite easy. If you just use a delta, you can just immediately doing these integrations. That is very easy. So I'm just trying to write down the result. Okay, so you can just evaluate this VPP prime is a very, very easy way in this using this delta. If it's not a delta function, that is could be pretty hard. Okay, so if you put this one here and moving this into this part. Oh, yes, and you can just get, I'm trying to derive that in this way, P square 2m. Let's try to group these energy terms and the kinetic energy terms together, minus E. Let's try to move this E here, that phi P. It's equal to, we still have a integral. Originally we have two-fold integral, but now we only have one-fold integral. But it's still integral. Okay, so now we need to just solve this equations. That is still a pretty hard equations. In the left-hand side, it's easy. So there's this P is no longer an operator. It's just a number, right? Because we are working in the momentum representations. But in the right-hand side is integral. We do not know how to solve this integral because to do this, to evaluate this integral, we need to solve what is a phi P. Without knowing this phi P, we cannot just get it. But we know that this is a functions, and that is a P prime dependent functions. So if you're doing the integral of the P prime, so the momentum terms should no longer there. So that is, we do not know what the number of that, but we must know that is a constant. This constant should be P independent constant. Okay, so that we just say that this C is not independent on P because all the P information is already integrated in this integral. So if we just trying to compare these and these, we're just trying to jump over the difficult part of this integral. But if we only have left-hand side here, right-hand side here, that's very easy. That we can just solve this phi P. It's just regular equations. C over, maybe let's try to make this a little bit nicer. P. Okay. So these, we can get these wave functions already. These wave functions, although this wave functions information is not complete because we still do not know what is a C is, but we know C is a constant. We also do not know what his energy is. So now we have two unknown constants. One is C, one is energy. Okay, so if we know these wave functions, we can just try to put this wave function back to this originally integral and see that whether it can be using the self-consistent method to solving the constant C and E. So in this case, what we're doing is that we just put this back, V0 to pi h bar minus. So this is 2mc over p square minus 2me. The dp is equal to c. So that is definitely, we can just try to remove c. In this case, c is constant from left and right hand side is just removed. So, and also we could just using our familiar, if E is smaller than 0, so that we want to just see whether we have like a bound state, so that the energy must be smaller than 0. So we can just using K is equal to or h bar. Okay, so that in this case, we need to do that is, if you just cancel this C to 1, something like that, we need to do that is minus here plus, so dp p square plus h bar square k square. So we're using k to replace e. So, and this integral should be able, we should be able to integrate that. So if you use mathematical, use other way, this integral is not very hard. So we can just evaluate this integral and put this integral into here. And then what is, we should be able to get what is k is. So this equation will determine a single k. If we get a single k, you should get a single e. So that is this quantization conditions. So this is a little bit strange, like to solve this problem. So we have these equations, we find that this is a constant, so we determine that it's a C, and we just solving these wave functions, and put this wave function here to just make it self-consistent. We just remove C, and we find that these equations, we have one equations, we have one unknown energy, unknown constant. This unknown constant is energy. If we just solving these equations, you should get the energy, so that you just only get one numbers. So this number is correspond to the bound energy of this bound states. Okay, good. So if that is for the bound state energies for the first part. Everything is easier. This part. Okay, you don't need to worry because you have record a video. Okay, so we just clean the screen and let's try to do the second section. Second part is calculate the wave functions. So I think we're almost there in the momentum representations. We're almost there. So we just calculate that is 5p. From the first one is already is a normalization constant. We do not do the normalizations. We get this. Right. So this is our wave functions. So what we need to do is need to do the normalizations. Normalization for in the momentum representations and in the position representation is the same. In momentum representations, this should be 1, right? So in this case, you should get A. So that is pretty standard. Okay, so that's the second one. The third one is calculate delta x and delta p in the momentum representations. Check the uncertainty rule. So that is typically that delta p is harder part, but in this case, delta p is the easier part because the p average is easy to do that, is p by p square dp. So that p is easy. If we do the p square, that here we only need to just changing the p square. So p is the easiest part. So you should be able to just get immediately. But in this time, x is harder part. X is basically I h bar d dp. So in this case, if you want to just calculate the x, you need to just do the derivative on the p, right? So I think there requires some calculations, but I think all these calculations, if you use a program, that should be relatively straightforward. Okay, so that is finally we'll just get the delta x, delta p. That is, it doesn't matter that is this delta x or delta p is derived in the position representations as we did before, or it is did in these momentum representations as we did now. So that is should be the same. So you should checking that is compare with h bar O2. So what is this is bigger or smaller? So that is checking the uncertainty principles. So that should be satisfied. Okay, so that is the part C. And the part D is that is finally, if we get the wave functions in the momentum representations, we want to just go into the position representations. What we need to do is that basically we already just shown that you need to do the Fourier transformations. So this dp, and IP for h4. So here is you might need like a little bit more complicated integral that in principle you can do that using mathematics, but actually it's not that easy because this is a complex integral instead of like real integral. So that is maybe in this problem that using hands is easier, but I think if you do not learn a lot of like path integral or something like that, it might be hard. So that is I just put it here. So when you do this Fourier transformations, you using this integral, and you should get the result immediately. So finally, you should get the result is k e minus kx. So you should get this very familiar result that we already derived in the lecture notes. So that this is coming from the exactly the same solutions as we derive everything in the position representations. Okay. So now we are trying to solve exactly the same problem with a very different starting point. We're starting in the momentum representations. And finally, we should get the same uncertainty principle, the same testing on the uncertainty principles, we should get the same wave functions. So like we have two choice. For this case, it's not that hard. I think when you just derive that, is basically you find that solving this problem in the position and the momentum is relatively similar. But if you are working on the relatively complicated like crystal structures, that these momentum representations must be much, much easier. Okay, any questions about this? Okay, so the next problem, problem 2 and 3, are two problems that is basically the same, but only the problem 2 is like a 2x2 matrix, and the problem 3 is a 3x3 matrix. So that is very important part. So I think we just spent a lot of like lectures to just go through this, how to do the eigenvalue problems in the matrix format. So I will just go through completely on problem 2, and I will ask you to do the problem 3. So that's basically they're exactly the same. The only difference is like it's a 2-dimension, one is a 3-dimension. So it's a little bit more complicated in the calculations, but all the steps are the same. So in the problem 2, that is a 2-level system, I did not give you the matrix format initially. I just give you the matrix operators, the Hamiltonian operators. So maybe that is even more one step further than step 3. Step 3, problem 3, I just give you the matrix directly. But the problem 2, I will ask you to evaluate the matrix format. So how to do that? I think that should be easy. So that is we should, if we want to just evaluate H11. So we should have a matrix. H matrix is H11, H12, H. If you just do not lazy, you can just use a H12 star, right? H22. So you do not need to just evaluate all of them. H11 is defined by H like this. We're just starting from left to 1, right is 1. Okay. So let's try to put these edge operators here. We find that we have epsilon. So like this 1, if we just get the first term, 1, 1, 1. This is the first term. The second term still the epsilon, and 1, 2, 2, 1, right? Third term is 1, 1, 2, 1. So last term is epsilon 1, 2, 1, 1. Okay, so next up, we need to use an orthonormal properties. This is 1, this is 1, good. So we have epsilon. So, but here is this orthogonal, this 0. This orthogonal, that's 0. So the second term is disappear. And here, this is 1, but this is 0. So that third term is disappear. And here, this is 1, but this is 0. So that fourth term is disappear. So that is only have 1 epsilon here. So the same thing that if you're just doing the H1, 2, so that is basically 1 H2, and H2, 2 is 2 H2. So you can use exactly the same method. You find that is the matrix element is not that complicated. And finally, we put all this result together, we can get an H matrix. This matrix is epsilon here, is 1, 1, 1, minus 1. So that is a Hamiltonian's. I will ask you to solve. So matrix format is here. So how to evaluate that is basically following this. We repeat this process 3 or 4 times. Okay, so and the next we need to just find these eigenvalues and eigenvectors. So eigenvalues is we need to just solve the deterministic equations, characteristic equations. So that is 1 minus lambda minus 1 minus lambda. This we copy is here. It should be equal to 0. Okay, and then it's relatively easy to get is lambda is equal to plus minus square root of 2 epsilon. So all we can just get rid of it. Okay, so that is easy. And the next, we should separate discuss like let's trying to have some space here. So that is we have lambda. The first eigenvalue is square root of 2 epsilon. So and that is we should get eigenvectors. If we put that into the original equations, and we should get the eigenvectors is 1 plus square root of 2, 1. So I did not do the normalizations. If you want, we can do the normalizations. But if lambda is equal to minus square root 2, so that is A2 is equal to, just write that down, 1 minus square root of 2, and 1. Okay, so I think up to now, is all the stuff is pretty standard, right? And let's try to keep the bottom part and erase this. Is there a quicker way to erase this? Okay, the computer's response is very slow. Okay, so I think we have a little bit space is good enough. So next is a relatively important is like that. We get the eigenvalues and eigenvectors. And this is basically finished the first part. And the second part is that let's try to calculate the time-dependent population transfer. So that is pretty important. Like, because we know that if our state is not prepared in the eigenstates, if a state is already just prepared in the eigenstate, or it's prepared in this state, or in this state, yes, you do not need to worry about anything because that it will stay in this state forever. So that eigenstate does not have any time-dependent population transfers. But here is typically the question is that all the population is prepared in state 1. This state 1 is neither here nor here, right? So state 1 is, what is state 1? State 1 here in the original like matrix format is basically 1, 0. So this is a state 1. This is the state 1 is in the original basis. Like the original basis defined. We just using this 1, 0 and 0, 1 to evaluate this matrix set. Right? So this is our initial states. or maybe let's try to using another part symbol to show that this wave functions at time t equals 0. That is in the 1, 0 states. So in this case, we need to try to write that in the superposition of the A1 and A2, right? If we can doing that, that will be good. So I can just jump over a lot of steps and trying to tell you that this is like this. I think that is also very easy. You can just try to using this one to just mixing A1, A2, you can get 1, 0. That is relatively easy to do that. But actually, let's try to jump some steps and we can get this. If we get this, that is all the later, the next step is relatively easy. So next step is minus E minus I lambda 1 t over h bar. This E minus I lambda 2 t over h bar. So here is lambda 1, here is lambda 2, right? So you get that one, you get the evolutions. And if you want to just do the population, you basically can just trying to square absolute value and square that. So you should be able to just get the result. Okay, so that now it seems like this two-level system very, very easy to find that if I just give you A1 and A2, and you can just find that like linear superposition of where A1 or A2, you can get that. But in the if a 3-level system, that is not that obvious. If you're 4-level, 5-level, that is more and more like harder and harder. You could just trying to directly solving the equations. You're just finding these superpositions and tuning the parameters and let the computer to just solve these linear equations. To do that, you can just get this result. But let's try to follow the recipe we just introduced in the lectures to showing that we need to just, if we can get a transformation matrix S, so in that case, we should be able to just obtain this mixing coefficient automatically. Let's see the transformation matrix. First, we cannot directly get the transformation matrix, but actually we get the reverse of transformation matrix. That is coming from what? It's coming from these eigenvectors in the old basis. So that is if this 1 plus square root of 2, 1, we just put these columns, and 1 minus square root of 2, these columns. So this is transformation matrix, but this is the inverse of the transformation matrix. And then you can just using any method to inverse that. You should get, let me just write this down. This is 1 minus 1 minus 1 plus square root 2, 1 plus square root 2. Okay, you can get this like transformation matrix. Okay, so next, if we have this transformation matrix, what we can do? We can just doing that is let's trying to writing a vectors is this vector is 1, 0. So this is initial conditions in the this is old basis, right? Oh, and we want to just get the vectors in the new basis. What we should do? We should just times s. Oh, why is s? Times s. If in the old basis vectors and we times s, that should go into the new vectors, new basis. What is equal to? So this s is just this matrix. Just times this matrix with this matrix, you should get. Let's try to do that here. So let's try to make everything clear. 1 minus 1 minus 1 plus 2, 1 plus square root of 2. Okay, that is equal to 1 over square root of 2. 1 minus 1. Okay, so that after this is in the old basis. This should be in the vectors in the new basis. So what that is basically in the new basis is here and here. So that is basically this is a mixing coefficient of here, and this is the mixing coefficient of here. So that's why we can just say that this is mixing coefficient is 1, this mixing coefficient is -1. So we get these vectors in the new basis. Okay, so that is the standard way is like that. If you're starting with initial conditions in the old basis, we need to do the transformations from the old basis to the new basis, because only in the new basis we can apply the time propagators, because that is eigenbasis. So we need to do these transformations, and finally how to find this coefficient. We starting from here and then transform here, and then we find the coefficient. We put this coefficient here, and we put the propagator here, and finally we can get the population distributions. Okay, questions?
We're saying that psi 0 is a superposition of the eigenstates. Why are they subtracted? Why is I1 subtracted?
Yeah, because this is we're using this transformation matrix to transform this 1, 0. Finally, we get this is 1, this is -1. Yeah.
But you're generalizing, shouldn't that be an addition of the two states? Because you're just writing it as A1 and A2.
No, A1 plus A2 and A1 minus A2 are two states. So if we're doing the A1 plus A2, that is there still could be another eigenstates, right? But this eigenstate is not like it's not this. It's not this. I think if I just ask you to do that from like if I just tell you that if y0, I just tell you the ground state, the initial state is this one, that should be plus. So, but if you're trying to create this 1, 0 state, that should be minus. Okay. Okay, any questions? Yeah, here is relatively obvious to see that is you can guess it's a plus or minus or something like that. But I think in the third 3-level system, you definitely need to using to evaluate this S-1 matrix and go into the S matrix, and then using these initial conditions to do the transformations, you get this coefficient, and then you can just write this. So that is basically the same procedures for the 3-level system, but actually that is not that obvious as this one. You can just guess. Okay. So that is for the third problems. Problem 3, I will not talking too much. I think at least in the first one, you should just following exactly the same procedures as a 2-level system. And for the second one, I just only give you some hint. It's like that. Is like whether when you're just doing this problem, you can just trying to follow the same procedures as step 1, but finally you'll find that maybe this initial state is isolated with all the other states. So this population could stay this state forever. So maybe you'll just find why is the reason is just already in this these Hamiltonians. So here is basically if you're starting from this third state, that basically correspond to the Hamiltonian in this part. So this third state, if that is coupling to the first state, that coupling is here. It's coupling to the second state, coupling is here. But if the both coupling is 0, so that means this state is basically the isolated state. That is not coupling to the first 2 states, and the population should not change for all the time. But I still suggest you to following the same procedures as the first part. And when you do that, you'll find that this state is already an eigenstate. If it's already an eigenstate, the population will not leave this state. The population will stay this state forever. So when you're just solving the eigenvalue problem, you find that one eigenvectors should be already like 0, 0, 1. If it's already eigenvectors, you do not need to worry about anything. So the population is stay there forever. Okay, the second part should be pretty quick. But first part, I think I just want to give you the exercise to go through them step by step. Okay, any questions about problem 3? Okay, so let's do the last problem. So it have several steps, and I trying to still trying to just walk through this. So first, let's trying to solve the problem in a very simple problem that is a harmonic oscillators. So, and if you're using the eigenstate of the harmonic oscillator as a basis, I think you definitely should be able to know what is the eigenstate of harmonic oscillator, right? Because we already solved that analytically expressions. So let's trying to write down the matrix of the H0 up to n equals 3, because this harmonic oscillator have n equal infinity, that we must truncate that to a small scale. So in the first part, let's trying to writing these Hamiltonians in the matrix format. So it should be relatively simple because that is like we know the eigenstate of H0. We're using the eigenstate of H0 as a basis. So that means first, these Hamiltonians must only have a diagonal terms. So all the off-diagonal terms must be 0. Otherwise, the basis is not eigenstates. So the eigenenergy, eigenvalue is eigenenergy. That we already know that. Half h bar omega, 3 half, 5 half. So I think let's try to make this a little bit larger. So we need to go into 3. So that is we have 4 state. So okay, so that is the diagonal terms is the eigenvalues of these problems, and the off diagonal terms must be 0. Okay, so that is a problem 1. So and then using the eigenstates of H0 as a basis, write the matrix form of X up to n equals 3. So now we're using these eigenstates as a basis, but in this case, let's try to write down the matrix format of X instead of H. In the H, like we're using these H operators, use the eigenstate of this one and writing the matrix, we know that it must be diagonal. But if you are writing like using this as a basis to writing the X operators, that's not always right. So how to do this? We need to using the ladder operators. We need using ladder operators. Okay. So in this case, let's try to expecting this as X operator. X is terms is X0, 1, 0, 0, X1, 1, X2, 2, X3, 3. But also here it's X0, 1, X0, 2, X0, 3, da, da, da. You have like maybe 4 by 4, like you have 16 matrix element, but also maybe you can count it because this part is complex conjugated than the top part. So that is maybe we do not need to evaluate this part. We only need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We only need 10, evaluate 10 matrix elements. Okay. So in this case, what we need to do that is we're using these operators, these ladder operators. We're trying to evaluate, for example, we can evaluate this. Okay, let's try to ignore the constant. That doesn't matter so much. A plus plus A minus 0. This is X0, 0. So obviously this is 0 because that will either decreasing or increasing, but this cannot just keep the same. So that is 0. So that is very, very easy, right? So you find that is X1, 1, X2, 2, X3, 3 are both 0 because this is X operators. We are not just connecting the same numbers from the left and right. Okay, so what is not 0? X0, 1 could be not 0 because this is 0, A plus plus A minus 1. So this term doesn't matter, but this term is not equal to 0. So this is maybe not equal to 0. And how about X0, 2 and X0, 3? That is must be 0 as well, right? Because it's only one raising and the lowering operators cannot connect 0, 2 and 0, 3. So that means there's maybe only X0, 1, X1, 2, and X2, 3 is not equal to 0. So only 3 terms is not equal to 0. Or definitely you just doing the complex conjugate in this part, there's only 3 terms is not equal to 0. Okay, so in this case, you are expecting to get X operators. We already shown that the diagonal terms must be 0. The off-diagonal term is, I will just write this down, 1 over square root 2. And here is 1. Here is 3 over 2. And all the others 0. But here is basically mirror here from 1 over square root 2, 1, all the other 0. Okay, so you get this matrix. Okay, so that is the second problem. And after that, we're doing that is let's trying to introduce the unharmonicities. So unharmonicities is basically we still keep this H0 as a 0 order Hamiltonians, but including some coupling, like maybe these unharmonicities can different mode of the harmonic oscillators. So definitely in this case, in the harmonic oscillator, this state, this state, this state, this state is basically isolated with each other. But if including the unharmonicities, maybe we could consider about some non-zero terms here, somewhere. So just coupling this state and these states. So that's trying to evaluate this non-like harmonic terms. So let's discard. I'll do that again. Okay, so let's trying to work on this unharmonicity term. Oh, what happened? Unharmonicity terms. Okay, the first step is trying to express these HA terms in terms of A plus and A minus, right? So that is trying to express that in terms A plus and A minus. So that is a lot of terms because this is X4. So X is A plus plus A minus. So if this one is basically should be equal to A plus, let's try to ignore all the constant here, power 4. So when you do that, you need to expand it all the terms, and you trying to make sure that A plus A minus is not equal to A minus A plus. So you cannot just changing the orders. So that means how many terms? I think this should be 2 to the 4 terms. That is 16 terms. Let's try to double check that. Yes, we should have 16 terms because we cannot combine any terms, any like different orders contribute to different terms. So in this case, like next step is trying to evaluate this matrix element of HA that should be the same as this is a 4x4 matrix. So let's try to do the delta n equals 0. It have like, maybe let's try delta n equals 0, delta n equals 1, delta n equals 2, and delta n equals 3. We need to have like this. What is delta n equal to 0? So that is basically correspond to this line, so diagonal terms. What is about n equal 1? That corresponds to this line. So this is n equals 0, delta n equals 0 line. This is delta n equal 1 line, and this is delta n equal 2 line. And here it's just one terms, that is delta n equals 3 line. So if we can just evaluate these 4 lines, we can just mirror that. The left bottom corner that is already can be calculated out. Okay, so let's see that. If that is all these 4 lines can be existed in this case, we could just use some symmetries. So we find that we have a 16 terms. So let's see that whether it can connect with delta n equal 1. So that means we need like if we have 4 terms, we need to increasing or decreasing by 1. That is not possible, right? We either have like 4 plus, that is basically increasing 4, or 3 plus and 1 minus, that's increasing by 2, or 2 plus 2 minus, that's increasing by 0. This is 4 plus, that's increasing by 4. So something like that. And also we can have minus 4 and minus 2 minus 4, right? But we cannot just make this plus and minus 1. So in that case, we cannot just make the rising operator is one more than the lowering operators. That is not working. So in this case, we can very safely to say that all these terms should be 0. All these terms should be 0. So that this line, we do not need to worry. And this line, we do not need to worry. So that this is 0, and all this line is 0, 0, 0. Okay, so next we need to just trying to evaluate delta n equal 0 line and delta n equal 2 lines. So this is a 4 ladder operators, 4 like the same identical ladder operators. That is not matter here because that is we only including 4 states. We cannot just connect it. If we just including 5 states, we should consider about that. So that we do not need to worry. And also we need to just collecting all these terms. How many terms here? And I think that we should have 1, 2, 3, 4. There is a 4 terms. So we have 16 terms. And 2 terms is here, 2 terms is here that we get rid of that. So that is we have 4 terms here, and we also need to just collecting these terms. I think this should be 10 terms. Let me see. 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5. Oh, this is 6 terms. Oh yeah, total is 10 terms. 6 terms. And here is 4 terms. 4 terms. But we do not need to evaluate this one. So we can just evaluate this side, upper like this corner is good enough. This left bottom corner is the same. So in this case, we need to separate these 16 terms into like delta n equal 0 terms and delta n equal 2 terms. So and then you can just try to evaluate that. So maybe I do not think I have time to just go through all this part, but let's try to give you examples. So for example, like, so this looks a lot terms, but actually it's not that hard as you thought. Oops, why did not? Oh. Okay, I think I can just write that on top. So for example, if you want to just get like this 2, 0. Oh, it's changing the color. Okay, that's fine. If you want to just get the 2, 0 terms. So that is what his contributions is a plus 3, a minus. That is definitely increasing 2. And also we can just add in this a plus 2, a minus, a plus. And also we can just have a plus, a minus, a plus square, and also plus a minus a plus square. It's cube. Okay, so that is only these 4 terms, right? There's no other terms. Like you see that is basically 3 plus here, 2 plus here, 1 plus here, and all the plus is in the bottom part. So that is, you can just try to expand it, these terms, but also you can also using some intuitions to just writing this directly, because each terms is the coefficient must be 1 because you do not combine any terms. So if you want to evaluate these 2, 0 terms, you need to just evaluate all these 4 terms and put them together. Okay. So I think maybe I will ask you to do that, but as usual, I want to just give you the answer. So that means definitely if you need to show me that your effort to get this answer. If you're just trying to copy this answer, I will not give you the full grade. So, but I indeed want to give you these answers. If you just find that your answer is wrong, is different. So you can just check what happens. So that is 3, 15, 39, 75. And definitely this 0, 0, 0, and this 0. So that this 0, 0, 0, and this 0. So we do not need to worry about that. 10, 6. It's the same here is 10. Okay, so that is basically our Hamiltonian should be here, and there are some mixing coefficient before that. Okay, so that is for the problem 3. Problem 4, that is initially all the population in the ground state of harmonic oscillators. So that means initially all the population in these states. And let's try to ask what's the time-dependent populations in all the other states. So if you just finish like the homework 3, the last part, you understand that basically if your state 1 is a ground state is connected to the third state through this. Okay, so find that the population of state 1 indeed can go into the state 3. So, but if you're trying to connect the state 1 into state 2, you find that the connection is 0. There's no connections. And also the same thing, state 1 to state 4, there's no connections. So that means you can just trying to reduce this matrix, this problem, because we know that the state 1 can go into state 3 through these channels. But state 1 cannot go into state 2 and state 4 because there's channels are 0. So that means why not just trying to keep the state 1 and keep this state 2 and state 4? That's no meaning because that is population. We're not touching that. So we can reduce this 4x4 matrix into the 2x2 matrix. So that is we can just trying to write this here. 39. And after that, you can only need to just solving this eigenvalue problem of this 2-level system instead of 4-level system, because the population will not have any chance to go into the second state and the fourth states. And after that, you can just doing the same thing as before, as a problem 2, to solving this 2x2 system, and you should be able to just get that. So I think maybe if you do not want to deal with constants, you can just setting all these constants is 1, and also setting this like a constant that is just before the unharmonicity part is 0.1. So that's showing that this perturbation is relatively small. I think that's good enough. You can just use some calculators to give the result. But anyway, I do not care about the numbers, but I indeed want you to just following these procedures to solve this problem. Okay, any questions? Okay, that's good. So let me just stop the record. I will just upload the to the YouTube this afternoon.